64. Describe how graphical methods can be used to determine the activation energy of a reaction from a series of data that includes the rate of reaction at varying temperatures. Okay. All right, so what I have is a little scenario here, right? We have some data. And generally speaking, if we are going to try to graph the data to find an activation energy, it's usually going to be your varying in temperatures and your rate constants. Now here, we could include the rate of reaction as well, but 9 times out of 10, they'll usually give you rate constant values, which has, implications for a rate of reaction because we're in kinetics. So just know that lowercase k is your rate constant. So we did a trial, right? We did 5 trials here where we just varied the temperature, right? And as the temperature seems to be increasing, seems that the K value is also increasing. The rate constant is also increasing. And just know that if you're increasing, the higher the rate, the higher the rate constant, the faster the rate of reaction. So we can say that, right? The higher the K value, the faster the rate is going to be. But now, if we took these and we tried to graph our graph, we wouldn't be able to get a linear line. We always like to work with linear lines here because that's how we can find out beautiful slopes, because it will be one single slope throughout a whole couple of trials. And from there, we could find out information. So the idea here is that if they give you temperature and rate constants, we can't just plug in temperatures and rate constants as our x and y's because you won't get that linear line. But what we can do is, if we want to see this beautiful linear line, we're going to have to turn all of our rate constants into their natural logs. Only when we do that is when we get our beautiful straight line. We have to do 2 things. We have to turn all of our rate constants into natural logs, ln, and we have to do the inverse of temperature, 1 over T. So you try it out. For all of your temperatures, take 1 divided by 555. What's that number? 1 divided by 595. 1 divided by 645. And then for your rate constants, you take the natural log of 3.52 times 10 to the negative 7th. Take the natural log, the ln, of 1.22 times 10 to the negative 6th. Now, what I'm going to do is I'm going to post up the answers. Let's see if yours match mine. Here they are, right here. Lovely. So in essence, if you have temperature versus rate constant, you have to transfer over your temperatures into 1 over. So if you do 1 divided by 555, you will get 1.8 times 10 to the negative 3rd. If you do 1 divided by 595, you get 1.74 times 10 to the negative 3. And then the same thing goes for here. If you take the ln of 3.52 times 10 to the negative 7th, you'll get negative 14.860. And from this graph and this graph only, since we have our 1 over t versus ln of k, those are the plots that you're going to plug in. Your 1 over t is always going to be your x-axis, and your ln of k is always going to be your y-axis. So think of this as each trial as x comma y. So 1 point would be 1.80 times 10 to the negative 3, negative 14.860. And then keep going, so on and so forth. So this one all the way down here, the negative 14.860, that would be your first point. And you actually kind of plot it like going backwards, it seems. But now the idea here is, okay, we plug this in, we put it into a beautiful graph. Here it is. You will see the linear line. But now how am I going to get that activation energy? Well, activation energy, just know, is always EA. And it turns out that the slope of this, if you find out that slope value, right? And how are we going to find out the slope value? We take 2 x's and 2 y's, right? The slope, oh boy. The slope is always to y2 minus y1 over x2 minus x1. Pick 2 points. It's a linear line, so it doesn't matter. They should all be on the same line. and find out your slope. Now, whatever your slope is, it's going to be a negative value because it's, decreasing. It's not increasing. So the slope would equal a negative because this is going to be a negative value, so you need to counteract that. But the slope actually equals to negative EA divided by R. Now, in this case, you have two options. Now, generally speaking, what I do is whenever we're using the R value, just know that that's a constant number. The constant R value always used is 8.314. And this is joules per mole times Kelvin. So that's why you got to have Kelvin as your temperature, because the rules of the R is it has to be in Kelvin. So now, if you're using that number, just know that your activation energy is always going to be in joules per mole, not kilojoules. So if you do need to find out kilojoules, you just take this value and divide it by 1,000. Another way of rearranging this formula is if we just cross multiply, right? EA equals negative slope times your R value. So either way, it doesn't matter which one you use. This one is easier because you're just solving for your activation energy. And just know that if you're using 8.314, that value is going to be in joules. So you just got to divide by 1,000 to get kilojoules. But that's basically it. So use your information. You got to plot 1 over temperature as your X, ln of K, ln of the rate constant, for your Y values. You will get a beautiful slope, linear slope, and your activation energy is just going to be that negative slope. This slope is going to be a negative value to begin with. So that's why a negative times a negative is going to be always an activation energy that's a positive. You should never get a negative activation energy. The activation energy should always be positive. All right? So if you do get a negative, maybe just swap the sign or just, double check yourself. But that's it. What'd you think? I hope this helped. Thank you for coming here. We love helping you guys out. Thank you so much. If you wouldn't mind hitting the subscribe button. We're almost at 40,000 subscribers at the moment. Thank you for that. And you guys rock. I really do appreciate all you guys. It's absolutely incredible what this community has done. Thank you for being so kind in the comments. And I'll talk to you soon, okay? All right. Bye-bye.